Good afternoon. Welcome to AVLeak, Fingerprinting Antivirus Emulators for Advanced Malware Evasion in Surfseas GH with Alex Bullazel. Just a couple of things before we get started. Don't forget to stop by the business hall that's located in Bayside AB during the day, and the welcome reception is tonight, 1730 to 1900 in the same room. Black Hat Arsenal is in the Palm Foyer on level 3. And the Pawnee Awards are tonight in Mandalay Bay, BCD at 1830. Finally, let's make sure we have our phones on so we're not making lots of noise. And also, these are being recorded, so when the Q&A time comes, please use the microphones that are placed in the aisles for questions. With that, Alex, it's yours.
Hi, so my name is Alex Bullazel, and I'm here to talk about AVLeak, Fingerprinting Antivirus Emulators for Advanced Malware Evasion. So a little introduction and an overview of the slides. I'm a recent graduate from Rensselaer Polytechnic Institute, RPI, and I worked on this as part of an undergraduate and then graduate research project under Dr. Bulent Jenner. And I also want to take this time to thank Jeremy Blackthorne, a PhD candidate under Dr. Jenner, who provided me with the original inspiration for this work and sponsored me doing it. So an outline of the presentation, just a little intro now. Then we're going to talk about the background and some prior work. Then our innovation with this tool, AVLeak. Then a live demo and some results, and then some conclusions. I also wanted to note we have a lot more content than I can fit in just a 25-minute briefing. So we are publishing next week at Usenix Woot, and we have a 15-page paper, a lot of citations, a lot of more material if you want to read that, and also a bunch of extra slides available and the version of this deck published online. So the problem. In the face of 1 million+ new malware samples a day, static signature-based malware detection is just dead. In response, AV and the anti-malware industry has turned to dynamic analysis, actually running binaries in these emulated environments and then seeing how they behave if they drop malware or they do heuristically malicious actions. And the problem with this is that malware that can detect that it's running in an emulator, in a VM, can then behave benignly and try to avoid detection. And it does that by finding what we call fingerprints of these systems. And over 80% of malware in the second half of 2015 exhibited evasive behavior. So there's been a lot of prior work on detecting things like VMware, QEMU, Zen, these high-end emulators, these things you use to actually do your own malware analysis, run in a debugger. But there's been little prior work on consumer AV emulators. So what I'm talking about is the emulators built into consumer AV products to protect your computers at home. So these systems are intuitively easy to evade. I've talked about this work many times to people, and they said, "Oh, well, that's super easy. It's a cakewalk," and that's true. But no one has actually gone and done this work and actually proven and shown ways of doing this and detecting these systems. So prior approaches for finding fingerprints, finding these ways of detecting these systems, are really inefficient. Either you have reverse engineering, which is just way too hard, incredibly difficult, or black box dynamic analysis, which I'm going to talk about in a minute, and that's just very slow and unwieldy. So our goal is to accelerate and automate this process. So what we built is AVLeak, a novel tool that allows researchers to easily and quickly extract these artifacts and these fingerprints from consumer AV emulators in order to create evasive malware. So now some background. So I mentioned these fingerprints, these ways we can detect these systems, and we categorize them into 6 categories. From the top, most trivially found, and also most trivially fixed. So things like hard-coded strings in the environment. If you have like a get computer name always returns a hard-coded value, we just check for that value. We know immediately we're in that emulator. Also super easy to fix. You just change that string and recompile your code. Then you have operating system functions that don't behave correctly. Network emulation, when they actually try to emulate network connectivity and they get that wrong. Timing skews and bugs, that's a known very hard problem. In fact, some folks from VMware published a paper a couple of years ago where they said, not only is it really not feasible to create these systems, they don't have any interest in even getting close, creating systems that are timing accurate. Process introspection, looking into your own process, your own behavior, your own register state. And then CPU red pills, very subtle artifacts related to the way CPU instructions behave on a real CPU versus an emulated one. So traditional malware sandboxes like QEMU and VMware, they are built in many layers. And the thing is, you can attack these underlying layers like QEMU. So if I have a bug in QEMU that I can use to detect it, then I can detect any malware sandbox built on top of QEMU. So they're actually, you have lots of systems that can detect anti-analysis, but it's also many layers of vulnerability in these systems. Consumer AV is different, that they're designed like this. You basically have on one side an x86 emulator, an emulated environment, and then also a user mode Windows API emulator, so emulating some subset of the Windows API. And they're just stepping through a malware binary, instruction by instruction with the x86 emulator, and then emulating certain Windows API calls when they happen. And then they have this fake environment that you can, when your malware does things like get username, they'll return a fake hard-coded username. And all they give is an analysis report that just says what malware they found. So there have been some prior approaches to evading them using what we call mutation, just packing a binary over and over again until it's no longer detected. This really doesn't require any intuitive, deep knowledge of the AVs. It just pack it until it doesn't get detected. There's also reversing. This is extremely challenging. You have to have expert knowledge of reversing itself, of AV, of Windows internals, of x86, all these layers of knowledge you have to have. And then you're looking at things that will crash IDA when you import them, have lots of anti-analysis, anti-debug, and then they'll also be frequently updated and you have to redo your work. That said, it has been done. Rolf Rolls, you can see here at the bottom, posted a Stack Overflow question, and he actually has done this, but Rolf is probably one of the best reverse engineers in the world, and incredibly talented. Not everyone is Rolf, and even Rolf doesn't have all the time in the world to do this. So some other prior approaches besides versing have been this kind of black box testing. This has been presented at a number of conferences in recent years. Most notably, the One Packard Rule Them All talk at Black Hat 2014 from Arna and Aladdin. And what these approaches look like is this. Begin with a question like, does this emulator emulate some arbitrary function X correctly? And then they'll create code that says, if it ran function X correctly or didn't return the expected value, I'm going to drop malware. Else I'm just going to exit. And you keep some encrypted piece of malware mapped to true and no malware to false. And you put this in the AV, and you choose I'm either drop malware or not drop malware. And the AV comes back and says, hey, we found malware or we didn't find malware. So this is a 1-bit side channel. It answers a single true or false query with each run, with each scan of a given piece of malware. But as you can see, this is very slow, and it's best suited to finding negative results, so things that are not emulated correctly. And now I want to talk about our innovation, which we call AVLeak. So our innovation on this prior approach. So what our innovation is what we exploit arbitrary malware detections to exfiltrate arbitrary specific byte sequences with each run, each scan. And we built this tool in C and Python, and we create fingerprints in hours, not seconds. So I want to show you what this looks like. So we begin by mapping malware samples to byte values, like this. So we would have A to Morris, and B to Code Red, and C to Zeus, and so forth. Here I just showed the ASCII range, but in actuality we use the full range of 0 to 256, or 255 rather, 0 to FF, and just map each of those to a given piece of malware, given signature. And in implementation, it gets a lot more complex, and you have signatures that aren't always detected and things like that. So there's a lot of actual stuff you have to work out, but this is the basic idea. We say Morris means A and Code Red means B, and so forth. And now we have a question. What's the username in this emulator? And let's say this emulator calls it emu. And then we run get username. And for each piece of malware, or for each byte in get username, we drop a piece of malware. So we drop E, the malware that stands for E in our table over there, then M, and then U. And now the AV comes back and it says, well, we found Sasser, Bagel, and Plaster, and we can correlate that across our table and see that inside our code saw EMU. And now we have a fingerprint inside this particular AV. The username is emu. We've done this very quickly, and we've avoided actually getting into the weeds and doing the reverse engineering, which is just too hard, as I talked about. So we wanted to demonstrate this technique against 4 consumer AVs. We chose Kaspersky, AVG, the Bitdefender engine, which is licensed out to 20 plus other AV products, as well as a number of high-end enterprise protection products. But this is also in other consumer AVs, most notably F-Secure relies on the Bitdefender emulator when they want to do this runtime dynamic analysis. And then also VBA. We found these by just uploading eCard droppers to VirusTotal. And we also wanted to know, we only tested 4 because we were going for a depth of actual tests and finding many fingerprints, not so much covering a wide range of AVs. This technique is generically applicable to any AV though, but just due to some complications like having to create individual VMs for each AV software is kind of difficult. So with that said, I want to jump right into a demo and show you guys what this looks like before I talk about some more of the results, because it is really cool. So here I have a demo, and this is in real time. I'm going to do that technique where we compile code, scan it with an AV, and then correlate the results back. So here you can see Kaspersky randomizes the module file name, the name of the program under analysis itself. And that's so you really can't print them in that way. So, one time it's jcrub and then TKD and so forth. So you can't fingerprint that. So that's actually really good. That avoids that fingerprinting. But then you see lots of these stupid things like VBA has this hard-coded value, 1, 2, 3, 4, 5, 6. Kaspersky's tick count after 10 calls to sleep is exactly 10 minutes later. In my testing, sleep has about a 15 millisecond overhead for the time it takes for it to call from sleep to sleepx, to trap into NTDLL, to go to the kernel, be paged out, and put to sleep, and actually woken up again. So that's some overhead. Kaspersky is just absolutely monotonic, just incremented by the number of times you slept. Here in Bitdefender, after 8.5 minutes of sleep, they messed up their calculations for how long sleep takes, and every 1 millisecond adds 15,000 milliseconds to the count. So you actually get an integer rollover, as you can see right there. And by the way, in hex, that's 1, 2, 3, 4, 5, 6, 7, 8. They just hard-coded that value. Now some process introspection artifacts. In Kaspersky, we looked at the kernel32.dll by doing load library and just grabbing the pointer there. And we started dumping bytes in memory in the Kaspersky emulator. And here we see it says KL auto-generated kernel32.dll. So we could just write malware that looks for KL auto-generated kernel32.dll and know we're running in Kaspersky. Now some more subtle artifacts here in Bitdefender. On a real system, you can see we access through the PEB, the process environment block. We crawled the loaded modules list to look at all DLLs loaded into our process space. And you can see here NTDLL, kernel base, and kernel 2. And right now in Bitdefender, it's dumping the Bitdefender ones. And as you'll see, it's going byte by byte by byte. That's because in real time, we're doing this process of compiling a piece of malware, running it through our system, and correlating the results back. And this is not a canned video demo. This is actually happening live. So every byte you see, that's a new piece of malware that we automatically compiled, scanned, and ran through. And as I said, we automate this all with a Python and C API. So even my test script, this is just an easy-to-use script that just prints out the data and runs different code using our API automatically. Don't really have time to get into the specifics of how the API is all implemented, given the limited time I have, but as you can see, it's super easy to do this. So now in Bitdefender, you'll see one artifact is that NTDLL has an entry point, but in the real system, it does not. So that's a giveaway that you're writing the Bitdefender emulator. Very subtle, though. And here, also the module, the file sizes are much smaller than the real NTDLL. But here, this third artifact is really interesting. There's a module called, the null pointer value. It's at base address CD. That's actually kernel memory. It's above the kernel user mode split at 7FFF. And then the size image is also CD. So this is some stupid hard-coded thing. And you could use this to detect that you're running a Bitdefender. This is just something that a programmer hard-coded in there. Now another very subtle class of artifacts, Windows heap allocations. When you allocate a block of size 0 with malloc or heap alloc, you actually get a block of size 16, as you can see demonstrated here. With each allocation, it's up by 16 or hex 10. But in VBA, there's a difference of 1,000 bytes for each allocation. And here in Bitdefender, there's a difference of only 8 bytes. You'll also note in Bitdefender, we used heap alloc deadbeef, so the handle to the process heap that we want to allocate on is not valid. But Bitdefender doesn't seem to check that and just gives you memory. In a real program, this would crash. Now, some more very subtle artifacts, CPU behavior. So we looked at how many CPU cycles using RDTSC to measure those cycles does a NOP take in Bitdefender. It takes 9. But so does a move, and so does a CPU ID, a much more complex instruction. And something really weird, really complex. How about lock and then exorps? This is like a SIMD instruction, long registers. This would take a long time on a real CPU. It still takes 9. So they just must have a CPU, increment tick count or increment CPU cycles function that just monotonically increases it by 9. So if you saw malware doing this, checking, is the CPU cycle 9, 9, 9, what would you even think? You wouldn't necessarily know what it's evading, what it's trying to evade. Even if you gave this to Bitdefender, probably one programmer wrote this once, just said, cycle count plus equals 9, and forgot about it. Super subtle, super hard to detect that this is an evasive behavior. And then running that same instruction in Kaspersky, VBA, and AVG, they all die. Just abort, don't find your malware, anything to just crash. So now we're going to look at CPU red pills, dumping out the CPU state after running a NOP on a real system. NOP is a no-op, nothing changes, as you can see. That's totally reasonable. And right now, in the background, we're dumping all these bytes of CPU, serializing the CPU out in Kaspersky. And you'll see here, ESI is just kind of all random. And this is a common thing. Kaspersky always does this. And once before you touch ESI, it just kind of is these random values. So literally, we save the state off, ran a NOP, save the state off again, and you see ESI got all weird. Don't know why. But again, you could have malware that looks for this. Does ESI change over the course of running a NOP? Now, in x86 in the standard call calling convention, the ECX EDX registers are volatile, meaning they can be smashed and changed during a function call. So in a real system, we set EBX and ECX and EDX to these values. And we see EBX is preserved, as the calling convention dictates, but ECX and EDX are smashed during a call to get current hardware profile. In Kaspersky, they remain the same. They're not smashed. So we set them right before that invocation, invoke the function, and we come back from the function, and they're still the same value. And this holds for any function running in Kaspersky. And you could tell that they're not actually really running the function. They're going and emulating that function in their custom code. In VBA, same deal. In AVG, we get this 7D39 thing, and then EDX is FFFFF, -1. It's always -1 in AVG. Now I wanted to talk about malware evasion, because that's the whole point of this work, is to create evasive malware that does not get detected while it's being running. So we wrote a dropper for the ecar file. It's a test file that's kind of a generic, should be detected by any malware company. So this is just an ecar dropper. And let's scan this with each of these AVs. So right now, it's running. So here, Kaspersky detected ecar. AVG detected ecar. or Bitdefender, which is actually where Bitdefender is licensed out to MZSoft and is actually very easy and very quick to use MZSoft, so we use MZSoft, but this is underlying the Bitdefender engine, ecar. And VBA also detects ecar. Now, I found with my work with AVLeak that these four AVs have these hard-coded computer names, NTFC, this thing, LXCZ, TZ, and main. So now we're just going to check, is the computer name one of these names? And if it is, we're just going to exit. Right? You can see right here. But if it's not that name, we're going to drop ecar. So this should evade all four of these AVs, and let's see if it does. So Kaspersky does not detect anything. And AVG does not detect anything, no infections. And Bitdefender does not detect anything. And VBA does not detect anything. So that's super easy to evade these things. Again, tons more artifacts than I can just present here, but just want to show you a demo, and then now I'm going to go through some more of the artifacts that I found that I couldn't show in this limited time. So the environmental artifacts, super easy to change, super easy to also use. So as I showed you, Kaspersky has randomized letters for the computer for the process name, but these other three AVs have these hard-coded values like test app, self.exe, malware sample.exe. And as I showed you, get computer name is also hard-coded in these AVs. So these are, again, super simple, kind of flashy and fun to look at, but not very advanced. We also built code to recursively dump the file system and registry of these AVs. And you see these funny things, like in Bitdefender, there's a couple strings on the file system. This is actually emulating, going through what files are on disk. You'll see these files that have batman.exe and things like that. So clearly some kind of joke. And you can even find there's like TZIPA de la Batman spike. But there's a common misspelling on people who have Romanian keyboards where the T and Z key are right next to each other. So it's very common to misspell and hit a T and then a Z. So you can even see that because they're a Romanian-based company. In Kaspersky, you have a bunch of files that are clearly someone smashing their hands on a QWERTY keyboard, like KOIO, 3 adjacent files or adjacent letters. The KL auto-generated thing in DLLs in Kaspersky. File Manager installs in Kaspersky and VBA. Other AV products, this was really funny. In Kaspersky, there's installs for over 20 plus other AV products in the program files directory. So they have like program files Kaspersky, program files Bitdefender, program files F-Secure. Presumably this is to goad malware into maybe behaving maliciously. See if the malware will, say, stat one of those directories and see if it exists, and then maybe choose to exit or not. So that could be a heuristic signal to the AV that this might be evasive malware or malicious malware. Network emulation. I didn't get to show this in the demo. I did present some of this work at ShmooCon, showed a network demo there. So in these three AVs, they're emulating network connectivity. So any network request you make automatically succeeds, and the HTTP request is 200 OK, even to totally invalid sites. You could even give things that's like totally malformed, not even a real URL. It'll still succeed. And actually, these things all return valid P files to you. So presumably that's another heuristic signal. Does this thing load this into memory? Does it write it to disk? That could be another signal that this might be a malware that downloads a stage 2. So they're going to, try to make the malware act out, try to make it show its malicious nature. Hard-coded start times, kind of the intersection of these environmental artifacts and the timing artifacts are hard-coded start times like this. So you just query the time, and in AVG you'll see, oh, it's May 23rd, 2011. If you see that, you know you're writing an AVG. And then you see Bitdefender has these APIs are broken. So it's 000 on January 1st, but then these other APIs break, and you get inconsistent times. VBA 000 again 2000, but it tells you different time with other APIs. So just totally broken, not even consistent across multiple ways of measuring time. Process introspection, I showed some of those artifacts related to looking at ourself in memory, looking at our register state after function calls, looking at data on the stack. But another one I didn't get to show here was fake library code. So we showed the module, the file header in memory with the KLR generated thing in the P file. But if we actually follow that a step further and do get proc address and see what bytes are at the actual return pointer, we'll find in all 4 AVs a similar pattern like this. So this is AVGs, but basically you have some unique instruction. So for AVG, it's lock, move, EBX, and then hex FF, a 1-byte number designating a library, and then a 2-byte number designating the ordinal export number of that function in the library. I can't demo it live here, but I've actually integrated Capstone with this tool with AVLeak, Capstone disassembly engine. I know the creator of that is here at Black Hat, and I talked earlier about his new project Keystone. We've integrated Capstone so we can live, as we dump data, disassemble it and see these patterns. So this is kind of like a hypercall in hypervisors, this unique instruction that when executed, the AV steps in, goes and emulates whatever function you wanted to run. So, if you wanted to run get current hardware profile, it would have, a 1 for NT or for kernel 32, and then some other number designating the function export number from that DLL. So you could actually use this and detect that you're writing an emulator. Now Kaspersky is unique that they actually, if you start looking for these bytes and enumerating through memory, they will hit you with a heuristic classification. It's saying it's heurScriptExploit.generic because real non-malicious programs shouldn't be doing something. This is kind of a weird behavior. CPU read post, as I showed, save the register state, dump it, and save it again. Now some conclusions for this work. So common themes, these simple environmental fingerprints are sufficient to create evasive malware. Really easy to create these evasive malware. These attempts to bait malware with things like giving you a P file when anytime you make a request, or having all these files in the file system. And then there's also a general lack of heuristic classification for malware when it behaves evasively. Other than that one thing with Kaspersky detecting you when you do in-memory DLL scanning. So one thing that was fun for me to do was to take these unique strings like KL auto-generated, or that the ghost file that cannot be found in Bitdefender, and Google them. And you actually find lots of these malware reports from places like Malware, VirusTotal, Total Hash, where they just got a binary, they ran strings on it, and they uploaded those results. So you can just see the output from strings that malware in the wild is looking for these unique values so it can be evasive. So malware authors already know about these and are using them in the wild. Now, more interesting than just random malware you find in Google was this piece of malware, the Evil Bunny, from the so-called Animal Farm APT. This was discovered by Marian Marszalek, I think 2014 or 2015. She might be here. She's here at the conference at least. And in 2011, it was evading Bitdefender. It would check, is its name test app? And if it was, it would not run. This is highly advanced APT level malware. And we also see below test app the AFYJEMV.exe. That kind of looks like those Kaspersky names that I jumped earlier. Presumably that might be some Kaspersky from maybe an earlier build that didn't randomize names per run, or they just say dumped out the data in one run and saved it off. One method of doing this I didn't touch on was simply taking a core dump from a running AV process. Once it's unpacked all these binaries, take a core dump, you run strings on it, and you'll find things like the username or stuff like that, but you're not going to find these more subtle artifacts like the red pills, like the timing skews. So they might have done that. I don't know. So we also talked about evasion. It's super easy to create this evasive malware. And in testing, when I did this, created about 30 different pieces of evasive malware with all different unique artifacts, 100% evasion rate in my testing. And now in terms of future work, obviously test more emulators, test more AVs. We'd also like to use AVLeak to find breakout exploits. This was actually the original motivation of this work when we began it at RPI. Jeremy Blackthorne, who was doing this work, he called it AV Escape. He said, can we find ways of breaking out of emulators? Can we use the fact that we're being scanned and trying to protect the system as a way of infecting the system? So in building and exploring this area of research and reversing these things, we realized it was actually really interesting to just try to evade them and just try to fingerprint them before we actually get to the, jump the gun and start actually breaking them. But this was, when we started this work 2 or 3 years ago as an undergraduate research project, this is what we wanted to do. And it kind of morphed into the evasion thing. But it would be really cool to come back to that. And Tavis Ormandy and Jukes and Korat have been demonstrating the viability of this kind of thing. So in conclusion, we've pushed the state of the art on emulator fingerprinting, given a categorization of these fingerprints as they apply to consumer AVs versus high-end emulators like Qemu and VMware, demonstrated real-world malware that's using them and how we can use them ourselves, and then discussed our directions in future research. I want to thank the RPI research team. This would not have been possible without them. A couple of these guys in the audience, Patrick, you're here? Oh, thanks, Patrick, and everyone who helped with this work. And then for some people who gave me help and inspiration, just little things here and there, and little tips and tricks. So thank you to everyone for that. Any questions? Again, also check out our paper at Woot if this interests you. Much more thorough, and I have a lot more information in the offline briefing. You have a Twitter handle, Kaspersky Labs, Pack in the K. Great music video if you've ever seen it. And while I take questions, I wanted to do something else, which was. I wanted to dump out the Kaspersky file system in the background while I talk. So this is actually going to enumerate through the entire Kaspersky file system and just dump it while I take questions. So thank you very much. So any questions? No? Is anyone? Okay. Well, thank you very much. I'll be here for a while. Oh, Mike has a question. Question over here.
Hello.
Hi.
So when you're dumping out information byte by byte, every time you're recompiling a new piece of malware and
That's
running
correct.
it and rescanning.
Yep.
When you're dumping out information such as pointers, did you run into any issues ensuring the exact same execution state?
So that is a concern. I did not run into any problems with that. Kaspersky in particular does randomized data per run, but Kaspersky has a very high output where they're able to detect 31 pieces of malware per run, so we can extract a large amount of data at a time. But we also obviously could brute force out. We could check the first byte and then say we'll dump the second byte if the first byte is the same, and the second byte if the third, second byte is the same, and so forth. But I did not run into that problem. I was worried I would.
Okay.
you.
When you were dumping out multiple bytes at once, did you have any, how did you ensure the ordering of the results correlating to the bytes that were being leaked out?
I found that the AVs detected the malware in the order was dropped, but there was a lot of engineering and making sure they detect drop malware every time and making sure it was reliable. A lot of back-end engineering on that.
All right, cool. Thanks.
Thanks.
Could you start again from the beginning because I don't understand anything?
So basically our innovation was that we use dropped malware names to represent individual byte values. And then we drop malware in order to extract fingerprints from these emulators to create evasive malware. Thank you.